5, 4, 3, 2, 1. Here we go. All right, it turns out KC and KP actually are related to each other through some funky math. Don't write anything down here, Ethan. Thank you. From the ideal gas law, we know that PV equals nRT. Rearranging it, we get P equals nRT over V. We already knew that. Plugging this stuff into the expression for Kp for each substance, the relationship between Kc and Kp becomes Kp equals Kc RT raised to the change in N. Now that is definitely something you should write down. I give you permission, Ethan. Yes. Yes, 0.0821 times the temperature raised to delta N. I spelled Kelvin wrong? What? Yes, sorry. All I heard was you spelled Kelvin wrong. Like it's not even on this slide. I really want to know if John gets the date. Well, we'll never know. Watch it be it's what's his face? Officer Thomas. That's his sub name. That he's just stoking chat hate for everything so he can bust people. All right. Now, I better not say more. He's in mine too. He knows, Fabian. He knows when you only want that on the test. Okay. I'm just joking, by the way. Joe Thomas is not in any of the group chats. I don't know. Okay, here we go. Delta N, this is important. It's moles. Look at the screen. Look at the screen. I know lots of things. Moles of gaseous product minus moles of gaseous reactant. They have to be gases or they don't have a Kp. So Kc and Kp would not relate anyway. Right. So if a problem asks you for Kp, you can solve it. And then it might ask for Kc as well, but it'll only give you pressures. And you're like, oh, I don't know what to do. Well, you plug it into this relationship. So this is the same equation, just rearranged for Kc. Kc equals Kp over RT raised to the change in moles, products minus reactants. You with me? Okay, here we go. So we have this, we'll use this equation a lot. It's the production of ammonia. We know that Kc is 10, just because I made that up, but I want to know what Kp is. So we just said Kp is equal to what? That's right, everyone. Thank you. We just said Kp was equal to Kc times RT raised to delta N, right? Moles of gas minus moles reactants.
Davidson, so you know how there's like undercover cops that look like teenagers? Have you ever had any of them in your class?
I have no idea. I don't think that really is the thing that happens here.
Think so?
I don't know how to answer that. I don't think so.
You don't think so? But there could be.
Yeah, definitely could be. Kids at these schools, they don't do drugs.
Yeah, kids at this school don't do drugs.
Yeah, Cooper.
Okay, that's a great question. Shh. Oh, it's not. It's a positive. No, it is a negative too. It's a negative. Okay, so the change of N equals the moles products. Moles reactants. So the products, it was 2. They're all gases. I didn't write it, but when I wrote this, I meant it. I'm sure that helped. All right. So you had 2, and then you have 1 plus 3. So where did I even put this? 2 minus 4 equals -2. Now do your order of operations right. You need to find the in parentheses first, raise it to the -2, and then multiply it by 10. How dare they? It was Jared Torrey, actually. Jared Torrey always writes stuff on them. Yep. I feel so bad that I thought you were an idiot last night. I didn't think you were an idiot. I just thought you were like super gutsy to just full send it right there in front of 300 of your peers.
I could see it.
I could see it too.
Really?
Yeah.
Hey,
All right.
remember what you did in the freaking-
Do we have an answer?
Yes.
It's 0.0167.
Well done, David. That's what I got.
Thank you. 0.0167.
What the heck are you?
After class. Okay, 30 seconds. Let me pause the video first.
The rose thing.
They have numbers out in front of the thing that are.
Yeah, well, the one was all nothing before, which was ones. It can be tricky. Just check it. All right, here we go. Equilibrium. Okay, that word. Equilibrium can be reached from either direction. All right, all this means is, remember our graph that went down like this and then up like this? All right, it could have come up like this and down like that. Like I could have had more reactants than products, or I could have had more reactants, or sorry, more products than the reactants. All that matters is we will end here, nice and parallel.
Yeah, nice and parallel.
We don't care if we started with too many reactants or too many products. It doesn't matter. It will reach equilibrium. All right, so that's all this is saying. This is data from the last 2 trials from the table on the previous slide. No matter where we start here, we would end all of them right here. Okay, so if I had a new one and I started here and here, then they'd be there. It's all saying. It doesn't matter which direction we go, equilibrium can be established. All right, so it does not matter whether we start with N2 and H2 or whether we start with NH3. We will have the same proportion of all 3 substances at equilibrium. It's kind of cool. None? None yet? He's trying to find out who the real John is.
He's on a mission.
I'm going to analyze.
Can I say actually?
I'll just text you and like, hey, Abs, who's John? And do you have address? Because I have some friends you can borrow one from if you're in a big hurry.
You genuinely think she doesn't have a dress for
No, I'm
Friday?
joking. I think she's fine. Okay. Scandal. Poor John. We got to find this guy and give him a hug. Do you know what we're talking about? Okay, you saw it too. Oh, you heard about it? Oh yeah, duh. Okay. And I thought she liked me. Thanks, Tia. You didn't have to do me like that. Okay. I know you weren't. It's good. Okay, here we go. This is important to your test. What does K mean? Kind of already said it, but if K is significantly larger than 1, the reaction is product favored. Kind of makes sense because the fraction, to get a number that's bigger than 1, you need a big number divided by a small number. Or you need a greater concentration of products than you do reactants.
the whole AP10 tab just goes and wrote this John.
But it's not John Nation.
Yeah, not that John, the other John. The real John.
All right.
John that's missing letters.
If k is less than 1. Now, be careful. That's not a negative number. We mean like 0.01 or 0.0001 or 1 times 10 to the negative third or 2.5 times 10 to the negative eighth. Okay, we'll never have a negative k, but we'll have things that are less than 1. Then we know the reaction is reactant favored, meaning you have more reactants at the end than you do products. And that makes sense math-wise. To get a small answer to this, you need a big number on the bottom and a little number on the top, comparatively. So these, if you just think about the math, you can usually reason through these. All right, what if k is 1, by the way? Then they're equal. Okay, here's a couple quick questions. All right, see if you can blow through these real fast. I'll pause it. Someone remind me, Nisha? All right, thank you, Nisha. Nisha's a lifesaver. 61. B can't be C because they're inverses of each other. And this one is a big number, so what all right, let's do this.
Yeah, there was no solving.
Okay. You're good. So this is kind of what Judah asked real quick. The equilibrium constant of a reaction in the reverse is the reciprocal of the equilibrium constant of the forward. Did it make sense how I explained that? So K forward would be your products over your reactants. K reverse, we're going the other direction, which would still be products over reactants, but the products were now really the reactants, and the reactants are really now the products. So the equation flips over, or we call it the reciprocal. Sort of all right with that? Okay. So that, I do believe that's on one of the tests. It's worth 3 points, and it's just hitting 1 over on your calculator. So make sure you get that point, those points. They're not too bad. Okay, I think the next one says if you double. All right, the equilibrium constant of a reaction that has been multiplied by a number is the equilibrium constant raised to a power that is equal to that number. This one's more, or sorry, less common. I was gonna say more uncommon, but that'd be a really stupid way to say it. But if we doubled all of this, then we square the equilibrium constant. And we do that because all of the exponents we raise it to, if you remember, are these, which would now be doubled, but they're exponents, so that's really squaring them. Yeah, this should be a caret and a 2. This is not real common, but it's just, it is what it is. All right, now the equilibrium constant for a net reaction made up of 2 or more steps is the product of the equilibrium constants for the individual steps. So if it's you have these 2 and it gives you like that these 2 make this third overall reaction, and it didn't give you Kc for the third, but it gave you these, you would just multiply them. Once again, not something we do a lot of. Yeah, hold on. Thanks, Fabian. Yeah, you guys only get them for 3 years. I'm on my 16th.
Imagine sharing the fall with them though.
It sucks.
Yeah, all the other teachers don't have to share a fall.
I think they can still hear him.
Yeah, they can.
You think the art room could hear him?
If they listen, if the windows are open now.
Yeah.
All right. This is a real simple process here, or concept here. Heterogeneous equilibrium. Heterogeneous means not the same. So it means when you have like a solid and a gas, this could be a liquid. It means when the states are not all the same. All right, they're pretty simple. The notes are right here. Well, don't write this yet down. Don't write down this yet. The concentrations of solids and liquids are essentially constant. Now remember, a liquid and a solution are different things. If it's a solution, it would be aqueous, not liquid. Both can be obtained by dividing the density of the substance by its molar mass, and both of these are constants at a constant temperature. So we don't worry about the concentration of them, which means they won't matter. Therefore, and I have no idea why I crossed that out, the concentrations of solids and liquids do not appear in the equilibrium expression. So if we had lead 2 chloride breaking apart to lead plus 2 chloride ions, we would say that the Kc is equal to Pb times Cl squared. And typically we'd say over PbCl2, but since it's a solid, it doesn't have a concentration, so it goes away. This is chapter 17, and these things are called KSP. If we did this, it would be KSP. It's called the solubility product. And it's called the solubility product because it is the solubility of these two things, and you multiply them by each other. Solubility product. So the KSP for PbCl2 would just be the concentration of Pb plus 2, and that's just its charge. It's not part of the math, and Cl minus squared. KSP is really the easiest of all of them because you never have to deal with the reactant because it's always a solid. You okay with that? Okay, this next slide is just some practice. So just quick, we don't have to do it, but solid, it'd be gone, right? So we'd end up with CO2 squared over CO squared. You with me? The only product that's a gas divided by the only product that was a gas. All right, this one, kids are like, this doesn't work. It only has this. Well, that's fine. It works. The Kc would just be CO2. So whatever that concentration was, that would be how we would find the equilibrium expression. All right. Now, solid. So we'd have the concentration of zinc plus 2 divided by the concentration of Cu plus 2. Fair enough? Don't put solids, don't put liquids, just put gases or aqueous substances.
Because you can't have a concentration of
Yep.
solid.
Yep. So this is kind of cool. If you have a vessel and it has just a little bit of calcium carbonate in it, it doesn't matter how much of that there is, the concentration of CO2 will be a constant. So you could have the same container and have just a tiny bit of CO2, and the concentration of this would be pressure, pressure, this is a gas. The pressure of CO2 above that would be the same because we don't care about the solid. The equilibrium expression is independent of the amount of CaCO3 present. All right, good enough. Okay, now, oh, well, that's exactly what I just said. I feel like I knew that was coming. So as long as some CaCO3 or CaO remain in the system, the amount of CO2 above the solid will remain the same. It's kind of interesting. Okay, now we're going to do a bunch of ice tables in the next 13 minutes. Remember, an ice table, I is your initial change equilibrium. This row is what you plug in to the K values or the mass action expression. The top row is the balanced equation. Fair enough? All right, I like these. So a closed system, and it will always usually say a closed system if it's on an actual real thing. A closed system initially containing 1.0 times 10 to the negative third, whatever, of H2 and 2 of I2 at 300 K is allowed to reach equilibrium. analysis shows the concentration of HI is 1.87 times 10 to the negative third. Calculate Kc at 3, 4, whatever. Okay, first off, the temperature is there because it makes this a true statement, but the temperature is not involved in this reaction unless they ask you to convert Kc and Kp. Okay, so I already drew the table around the balanced equation. So, uh-oh. Sorry. You all right over there? No. Oh, my daughter. Carly Davidson, my daughter. Okay, initial H2 is right here. Are you okay if I just write 0.001? And this is 0.002. That's what this is in normal land. Does it say it contained any HI to start? No, so that's 0. Not always. It could say a closed system initially contained this of that, and this of HI. It could. It doesn't normally, but it can. Okay. And then the next thing says at equilibrium, HI is 1.87 times 10 to the negative third. So that would be, no, it's still to the negative third.
Wait, it says HI.
Oh, thank you. My fault. Thank you. Okay. So the HI is 0.00187. That makes sense because this should have gone down, not up. Okay. So what's my change here?
0.00187 positive.
Okay, well, it depends. Depends on the coefficient. So both of these, they decrease 1/2 of this. Their rate is 1/2 as much as HI. You with me on how I got that? Okay. So I don't know what 0.00187 divided by 2 is, but that's what this number is. 0.000, right? 935. And those are both negatives. How do I know they're negatives?
Because they're going down. They're all going down.
Okay, because reactants decrease, products increase. Okay, so then I do this math. What is the equilibrium for H2? Thank you. And this would be, that's the other one? Okay, this one is 4 zeros? Okay. Did this one have 3 zeros then? Okay, okay. Okay, we're good. Okay, then you have the equilibrium values. You got to make sure you know the equilibrium expression. So this is molarity. So this is Kc equals HI squared over H2 to the first, I2 to the first. How is her dancing? Uh-oh. No, it's because when COVID hit, I took 4 iPads home. I'm glad. Whoa, hey. I got great video of Derek at the dance.
Oh, yeah, Derek was.
Derek knows how to get down.
Yeah, Derek was getting down.
He, at the end, he came up, he's like, I'm hot. He was soaking wet. I was like, oh boy. That was good for the dad because I'm like, well, there won't be any kissing, that's for sure. Sorry, I didn't say that. Don't tell him I said that. I think he's tired of me in his life. I didn't. No, I'm just kidding. What's this number? What's that, Caitlin? Do we get an agreement to 50.51? Okay, next. Do on your own. It can't be 1.4. Okay, and that's a negative. This would be negative 1.2, right? Positive 2.4, right? 1.3, 2.4. Plug it in.
Oh, shoot, what is R again?
0.821. So we plug this into the equilibrium expression. We have 2.4 squared over 0.85, and that was squared, right? 1.3, which was not, correct? 6.13, is that what you said?
What do you add? Kelvin?
273. Is it not in Kelvin? Oh, it's not, is it?
Yeah.
All right, the bell will ring, but our KP was equal to our KC, which was 6.13, 0.821. Whoops, whoops, whoops. Times 0.0821 times 298 raised to the -1, right?
Why would it be -1?
Because it's 2 moles minus 3 moles.
Oh,
Moles of products minus moles of reactants. And what did KC end up? Or sorry, that was KC.
If I got 6.9 for the first one.
There's something wrong. That'd be too far off.